Welcome to ES 310 Lesson 24. Today we will continue with the analysis of the kinetics of rigid body motion by looking at bodies that are rotating around a fixed point. In order to do this analysis, we need to introduce or reintroduce the concept of mass moment of inertia for the various objects. More information about this topic can be found in Hibbeler's Dynamics textbook, Chapter 17, Sections 1 through 4. As a reminder from statics, where we first saw mass moment of inertia, it's defined as the resistance of a body to angular acceleration. Since mass is the resistance of a body to linear acceleration, mass moment of inertia can be thought of as the rotational version of mass. The equation for mass moment of inertia is the integral of r squared dm. If we write dm as rho dv, then this integral can be written as rho times the integral of r squared dv. Conventions for mass moment of inertia says that if we have planar motion, that is motion that acts only in one plane, then I passes through the center of gravity and is perpendicular to that plane. The units for I are either kilograms meters squared or slugs foot squared. There are several ways of finding the mass moment of inertia I. The most general is through integration. So there's two ways we can look at this integration. In the shell element method, we draw a shell which is a cylindrical element that starts with a radius of 0 and then moves outwards until it completely fills the volume that we're interested in. The general equation I equals the integral of r squared rho dv is used here, where dv is written as the circumference of the shell, 2 pi r, times the thickness of the shell, dr, times the height of the shell, h. So in the case that we see in this figure, we have 2 pi, the radius is y, dy is the thickness, and z is the height. If we look at the same volume using a disk element, we have a small disk element that we start at one end and sweep through the entire volume. So in this case, we're going to use the expression I is equal to the integral of di, and we're going to look at di as the moment of inertia of a disk. And the moment of inertia of a disk is 1/2 of the mass times the radius of that disk squared. In this case, we have a dm, a differential sized mass, and so we have 1/2 dm y squared, where y is the radius of the disk. We can rewrite dm as rho times dv, so we've got pi times the cross-sectional area, which is y r squared, times the thickness dz gives us dv, times the radius squared again, y squared. Then we plug this into the integral and take that integral to find the total moment of inertia I. This is around the z-axis in both cases. We can also find mass moment of inertias for common shapes by looking things up in the table. So we have a variety of common shapes. In this table, we've got spheres, cylinders, perfectly slender cylinders, thin rings. This is the disk that we used in the previous derivation, and things of this sort. Notice that to use this table, we need to pay attention to the axis that we're working around. So for example, IXX and IYY are around these perpendicular axes to the cylinder. IZZ is the axis parallel to the cylinder. We also have some of these that are given at two different axes. For example, this disk, we can have this XYZ axis, which go through the center, or we have a YZ prime axis, which goes through a point on the edge of the disk. Similarly, the slender rod has expressions given for an axis through the center of the rod, as well as an axis through the end of the rod. So let's take an example in which we will find the mass moment of inertia through integration. And I'm going to do this using both the disk method and the shell method, so that you can see a reminder of how this works in both cases. And so we'll start with the shell method. In the shell method, we have that I is equal to r squared rho dv. The shell is going to look something like this, right, with a circle here and the same edge over here. Alright, so that's our shell. And so dv then is going to be, well, first of all, the radius is in the x direction. So r is going to equal x. So we've got x squared rho. And then dv is going to be the circumference, pi, 2 pi x, times the thickness, dx, times the height of this cylinder. Well, the height of this cylinder is 3 minus, that's h, right? So 3 minus the value of x at that point. So we have 3, or the value of y at that point. So we have 3 minus y. Now, we need to rewrite y in terms of x so that we only have one variable in this integral, but we have the expression for y in terms of x. So if y cubed is equal to 9x, then y is equal to 9x to the 1/3. And we can plug that in over here, and we get, pulling the constants out, 2 pi rho times the integral of x squared times, actually, x cubed, because there's this x plus that and that x, so x cubed times 3 minus 9x to the 1/3 dx. We can further analyze this and simplify it. We get 2 pi rho integral of 3x cubed minus 9 to the 1/3. X cubed is the same as 9 over 3, so we get x to the 10 over 3 dx, and then we can take this integral, and we're going to take this integral for the entire sweep. So we're sweeping in x, so we're going to go from 0 out to x equal to 3, so this integral is from 0 to 3. We can take this integral, we get 2 pi rho times the integral of 3x cubed is 3/4 x to the 4th, minus 9 to the 1/3, and then the inverse of this plus 1, so this is going to be 3 over 13 times x to the 13 over 3. Evaluated from 0 to 3, you plug in 3 into this equation, and you will get 29.4 rho. So if we know rho, which we can find from this gamma, then we can find our mass moment of inertia. Now let's do the same thing using the disk method, which is actually the easier method here. So the disk method is this circular disk that we sweep up and down, up through y. So I is going to equal the integral of di, and di is equal to the mass moment of inertia of this disk. Well, the mass moment of inertia of a disk around the z-axis through its center is 1/2 mr squared. So that's going to be 1/2 of dm r squared. Well, dm is rho dv, so this is going to equal 1/2 of rho dv r squared, so 1/2 of rho. Now dv is the volume of that disk, so we have pi r squared times the thickness of that disk times the thickness of that disk times the r squared that's still there. Well, in this case, r is still equal to x, so we get 1/2 rho pi r to the 4th x to the 4th, pi x to the 4th dy. Now we want to write things in terms of y since our differential variable is y. So we get our final integral of 1/2 of rho pi x is equal to 1/9 of y cubed. So this is 1/9 to the 4th times y cubed to the 4th, which is y to the 12th dy. Then we can take the integral of this. We get, so 1/2 rho pi 1 over 9 to the 4th are all constants. The integral of y to the 12th dy is 1 over 13 y to the 13th dy. Our limits of integration takes us from down here to up there, so 0 to 3. And plugging in 3, then we get, so this is evaluated from 0 to 3. There isn't actually a dy there because we've taken the integral. And we get 29.4 rho. So same as we got before. So two methods of doing the same thing. The more of these problems that you work, the better you get at figuring out which method is the easiest method for various shapes. Parallel axis theorem says that once we have I around the center of mass, we can find I around any other point by adding the total mass times the distance from the center of mass to the point we're interested in. So find I around the center of mass and then shift it by md squared. Notice this has to be I around the center of mass. So that allows us, by integration or by using the tables, to find I around any point we might be interested in. Some other common definitions. Sometimes the problem will give you moment of inertia. Other times it will give it to you in terms of radius of gyration. They're really giving us the same information because the moment of inertia is defined as mass times the radius of gyration squared. So whether it gives us the radius of gyration or the moment of inertia, we can find the other. It's a measure of the distribution of mass around the axis of rotation. So it's a distance measure as to where that mass is relative to this axis that you're rotating around. You could also use composite bodies. So if you can find I for each member of the body, so each sub-body, then you can combine them all. So you find each one around a given point, so shift them all to the same point, and then add them all together and subtract any holes. The key is they all have to be around the same point in order for this to work. You're going to use parallel axis theorem to shift all of the radius of gyrations to the same point. So let's see an example of this where we're going to use our tables and composite bodies to find the mass and moment of inertia of this wheel. So we know that the wheel has a ring that's a mass of 10 kilograms and it has 4 spokes that have a mass of 2 kilograms each. So the wheel moment of inertia around the center, O, is equal to, this is a thin ring, so if we go look at the expression for a thin ring, around the axis out of plane of that ring is mr squared. So that is equal to mr squared. M is 10, r is 0.5 squared. Then we have the moment of inertia of the spoke, a single spoke around point O. So each one of these little things is a spoke, right? So a spoke is a slender rod, and we're interested in the point on the end of the slender rod. So if we go and look at our equation, slender rod, the end point is the x prime, y prime axis. So we're looking for either x prime or y prime, which are these. So that's 1/3 ml squared. So this is 1/3 ml squared, different m, of course. This is m of the spoke, this is m of the wheel. So we've got m of the 1/3 of 2, L is 0.5 squared. And there are 4 of those. So the total I around point O is equal to 10 times 0.5 squared plus 1/3 times 2 times 0.5 squared times 4, because there are 4 of them. So this, if you plug it into your calculator, gives you 3.167. Then we need to shift this because we're interested in point A, not the center point O. So So we found it around the center of mass. We can shift it to any other point we're interested in. So IA is going to equal IO plus the total mass times the distance that we shift squared. So this is 3.167 plus the total mass, which is 10 plus 4 times 2, or 18, times the distance we move, which is 0.5, squared. We plug these in and we get 7.667, and the units are kilogram meters squared. So now that we've covered mass moment of inertia, we can use that mass moment of inertia to help us solve for equations of motion involving rotation, where that rotation is around a fixed point, which we will call O. In that case, we're interested again in the motion of the center of gravity. So the center of gravity moves in an arc around O. So we're going to use the normal tangential coordinate systems. So we're going to use the normal tangential coordinate systems. So we need to change those to T's from R's. Alright, so in the normal tangential coordinate system, the force is in the normal direction, which is pointing towards the fixed point. It's going to equal mass times the acceleration of point G in the normal direction. And the normal acceleration then is this omega squared times the radius 2g. Then we also have the sum of forces in the tangential direction, which is causing the tangential acceleration. And the tangential acceleration is alpha times rg. Moment-wise, we have that the sum of the moments at g are equal to the mass moment of inertia at g times alpha, or the sum of the moments at O, the still point, is equal to the mass moment of inertia around the still point times alpha. So notice you have two options: either your center of mass, or you have your stationary point as the points that you can add moments around. Your process here is to draw a free body diagram, establish your coordinates and draw your forces, indicate your acceleration directions. And then use your equations of motion, which is shown in the orange box, and use kinematics if necessary. If you're asked about velocities or times, you can use kinematics once you've solved the kinetics. So let's take an example of this. We have this wheel that is on a support that is massless. And the wheel starts spinning, and then we lower that wheel into the ground, and there's friction on the ground which slows the wheel down, and we're asked to figure out how long does it take for the wheel to slow to 0, and how much force is occurring at the pin at this point. So first of all, let's draw a free body diagram of our wheel. So if this is our wheel, we have, it's moving in an omega here, we have a friction on this wheel. Which way does the friction go? It goes opposite the direction of motion of a point. So if the wheel is turning clockwise, then this point is moving to the left. So friction then would be acting to the right. So that's friction. There's also a normal force on the wheel because it's sitting on the floor. That's our normal force. We have a weight on the wheel, which acts straight down, and then we have this force that's being caused by FAB. Now, we can simplify this force because we know that FAB is massless, and it only has two forces. It has a force at A and it has a force at B. There's no other forces along here. So it's an example of a two-force member, which we saw in statics, and we know that forces on a two-force member act in the direction from one end to the other. So in this case, this force is going to act from B to A in this direction. And so we have information then about that direction because this is 3 and this is 4, so the hypotenuse must be 5. So the triangle here is going to be 3, 4, a 3, 4, 5 triangle, and that gives us direction information about this force AB. So we have our equation of motion, or we have our free body diagram drawn. This point in the middle is our center of mass, and so we can look at the equations of motion for this situation. So the sum of the forces in the x direction at the center of mass is going to equal, or the sum of the forces in the x direction, we've got the friction force minus FAB times 4/5, which is the x part of that force, is equal to 0. And then we have in the y direction, where up is defined as positive, we have the normal force acting up minus the weight acting down plus FAB times 3/5, which is the x or the y part of FAB. That is also equal to 0, because this point is not only the center of mass, it's also at the stationary point. So that means then we also have MB, and MB around M around B is allowed because it is both the center of mass and the stationary point, each of which we can use. So the moments around B, the only one of these forces that cause the moment is the friction. Everything else passes through point B. So we have the friction times the distance, which is 0.2, is equal to IB, the moment of inertia around of I, times alpha, where this alpha, the same direction of omega, is negative. So then we can use our knowledge. We know that friction is equal to mu times n, so this is equal to 0.5 times n. So we can plug some things in here. We get 0.5 times the normal force times 0.2 is equal to IB. Let's take a look at IB. They give us KB, so they give us the radius of gyration. If we have KB is equal to 0.15, then IB is equal to the mass times KB squared, which gives us 0.5625. So this is equal to 0.5625 times alpha. We don't know n, but we can find n, because up here we have two equations and two unknowns. Two equations, two unknowns, so you can plug them into your calculator and you will get that n is equal to 178.3 and FAB is equal to 111.5. So now, knowing n, we can plug n in over here and we can solve for alpha being equal to negative 31.7. So it's slowing down at 31.7 radians per second squared. Now what we're trying to find, though, is the time necessary, the time required for the motion to stop. That is a kinematic question, right? So we're given an acceleration, we're asked information about a time. That means we turn to our kinematics. We have an equation in kinematics that tells us that the final omega is equal to the initial omega plus alpha times t. Well, the final omega is it stops. That's 0. The initial omega was given. It's 40. We know alpha. We can find t. So alpha is minus 31.7 times t. Solve for t, and we get 1.26 seconds.